Welcome to SpaceTime Cafe, episode 40. Today, primes, superconductors, and the secret geometry of logic revealed.
Welcome back to the deep dive. Today, we are strapping in for something pretty wild, conceptually speaking. One of the most ambitious journeys we've taken through a stack of sources.
Yeah, it's quite something. We're basically starting with a thought experiment. You know, the kind of thing you might doodle on a napkin.
Exactly. And somehow we're going to end up, potentially at a unified theory of physics. It sounds crazy, but stick with us.
It really is this convergence point. You know, physicists, mathematicians, they've been chasing this kind of unification for decades.
Yeah.
And the material we're looking at today, it seems to actually knit together things like abstract number theory.
Which is already mind-bending.
Right. And condensed matter physics.
Yeah.
Specifically superconductivity. And then even connects it to the cutting edge of geometric theory.
Okay, let's paint the picture first.
Yeah.
Imagine you have a necklace. Simple, right? A circle.
Okay.
But the beads aren't just red or blue. They're colored by the prime numbers. So bead 1 is 2, bead 2 is 3, then 5, 7, 11.
Yeah.
All the way around in sequence.
Got it. Primes as beads.
And the puzzle, seemingly simple, is, can you cut this necklace, maybe with a few cuts, to divide it perfectly, fairly among, let's say, 4 people?
And fairly. Here's the key, right? It's not just about everyone getting the same number of beads.
No, that would be too easy.
Fairness here means everyone gets exactly the same number of 2 beads, exactly the same number of 3 beads, the same number of 5 beads for every single prime represented.
An equal share of each color, essentially, this little setup. It's called the prime necklace problem.
Sounds simple enough on the surface.
Deceptively simple.
Yeah.
Because our mission today, the deep dive we're taking, is to unpack this really quite astonishing finding that this humble puzzle, it's actually a gateway.
A gateway to what, though?
Well, we're going to show you how the distribution of primes, when you look at it in a very specific way, starts to behave like a discrete anti-superconductor.
Anti-superconductor. Okay, that's a term I wasn't expecting next to primes.
Right. And that the very act of finding those fair cuts, mathematically speaking, it actually defines something called a non-commutative space.
Which is, that's deep in the weeds of modern geometry and physics. The kind of structures they think might underlie everything.
Exactly. So get ready for a journey where the famous, chaos of prime numbers, how they seem so random.
Yeah, completely unpredictable.
Turns out to maybe be an unexpected, almost perfect hidden order. An order that, and this is crucial, seems to only reveal itself through a model of intelligent, maybe even predictive search.
Okay. Chaos, order, primes, superconductors, non-commutative geometry. Let's dive in.
All right, let's start with the basics. Before we even get to the primes, let's talk about the classic necklace problem. Just regular beads, different colors. Maybe red, blue, green.
Okay, simpler case.
Yeah. And you want to divide them fairly, say, among 4 people.
Mm-hmm.
How do mathematicians know, with absolute certainty, that a fair split is always possible, no matter how jumbled the colors are?
That's where topology comes in. It's a really beautiful piece of mathematics.
Topology. So the math of shapes and spaces that don't change when you stretch or squish them.
Exactly. And specifically, there's this powerful theorem called the Borsuk-Ulam theorem. It's kind of profound.
So this theorem somehow forces fairness onto the necklace.
In a way, yes. Imagine a sphere like the Earth. The Borsuk-Ulam theorem basically says if you have any continuous function mapping points on that sphere to, say, a 2D plane, like temperature and pressure at every point.
Okay.
There must be at least one pair of points exactly opposite each other, antipodal points that have the exact same values for both temperature and pressure.
Wow. Okay, how does that relate to beads?
Well, you can define a function that measures the imbalance for each color bead for any possible set of cuts. The theorem guarantees there must be a set of cuts where the imbalance for every single color is simultaneously 0.
So a perfectly fair division must exist. Topology guarantees it.
It's a guarantee of existence, yes. It tells you it's out there.
But it doesn't tell you where the cuts are. It doesn't give you the map.
Precisely. And it also gives you an upper bound on the number of cuts you might need. If you have taller colors and people, you won't need more than taller times K1 cuts.
Okay, so the guarantee is solid for regular colors.
Yeah.
But then we hit the primes.
And that's the prime chaos challenge. This is where the smooth topological promise kind of slams into a wall.
Right, because primes are anything but smooth or regular.
Yeah.
Their distribution is famously erratic. The gaps between them are unpredictable. I mean, the Riemann hypothesis is still unsolved because of this.
Exactly. So if you try to use the prime values themselves, the number 2, the number 3, the number 5 as your colors.
It just falls apart. Why did that chaos break the guarantee?
Well, the guarantee itself, topologically, might still hold in some abstract sense, but practically, using the prime value as the color is computationally a nightmare. The density fluctuates wildly.
Like the prime 2 only shows up once.
Right. But then you look way out, like between 1,000,000 and 1,100,000, and the density of primes there is totally different than between 0 and 100. These huge gaps in clusters, they make any idea of a uniform color distribution based on value completely unstable. You can't divide them fairly that way.
So the breakthrough wasn't trying to tame that chaos. It was sidestepping it, using something the researchers called modular rhythm engineering.
Yes. This is the first really big conceptual leap. Forget the prime value, forget how big the prime is.
Okay, so what do you focus on?
You focus entirely on its index, its position in the prime sequence. P at y is 2, P to 2 is 3, P2 is 3, 3 is 5, T at y is 7, and so on. The sequence of indices 1, 2, 3, 4, 5, that sequence is perfectly regular, perfectly predictable.
Ah, okay. So you're basically ignoring the bead's inherent number property and just labeling it based on where it sits in the line. You're imposing an external rhythm.
That's a great way to put it. Imposing an external rhythm. And this let them define what they call the prime phase embedding equation. It looks like sex-axis is commode KD9.
Okay, let's break that down. Calors is the number of people we're dividing among, like 4.
Right, the modulus.
The modulus is the index, the position, first prime, second prime, etc.
Yep.
What's $6 and what's that?
TAS. So $6 is the result. It's the color class or the modular segment that prime gets assigned to. If K to the 4 is 3, then $6 will always be 0, 1, 2, or 3.
So every prime gets put into one of 4 bins, essentially.
Exactly. And because the input sequence, the index $2, 2, 3, 4, 5, is perfectly uniform, when you map it cyclically using the modulo to dollars, the output distribution of $6 is also forced to be perfectly uniform, or very close to it, for large numbers of primes.
Wow. So this guarantees perfect modular fairness. If you have non-primes total, and $9 happens to be a multiple of $, you know exactly how many primes land in bin 0, bin 1, bin 2, and bin 3.
Precisely. For a reasonably long necklace, the distribution across the Doppler classes becomes almost perfectly uniform. It completely smooths out the chaos caused by the prime values and gaps.
And that battle factor, the phase shifter, what's its job?
PAI is like a tuning knob. It's often chosen based on principles related to things like the golden ratio or other irrational numbers. Its role is to ensure maximum dispersion to kind of scramble the index Eilers before the modulo operation so you don't get unwanted correlations or simple patterns. It helps make the distribution into the Dahligens as uniform as possible.
Okay, this is really clever. You take this notoriously chaotic sequence,
Just primes.
you ignore their values, focus only on their perfectly regular order, and use this modular arithmetic trick to force them into perfectly balanced categories.
You've basically engineered order out of apparent chaos by changing your frame of reference.
It's like finding a hidden rhythm that was there all along, just obscured by the noisy prime values themselves. And this structured setup, this perfect modular fairness, is what unlocks the door to all the quantum stuff later, right?
Absolutely. If the underlying colors were still chaotic, none of the subsequent operator math or physics analogies would work. You need this foundation of perfect modular rhythm to build upon. It creates a solvable, structured problem space.
Okay, so step 1 is complete. We've tamed the primes, at least in terms of their distribution into these dollar categories using the index trick. And topology, the Borsuk-Ulam theorem, tells us a perfectly fair cut must exist somewhere.
Right. Existence guaranteed, categories defined.
But, knowing something exists and actually finding it are 2 totally different problems, especially in what must be a huge, complicated search space of possible cuts.
Exactly. How does an agent think of an AI, or maybe even a simplified model of a cognitive system? How does it efficiently navigate this space to find the optimal cuts?
And this is where the sources introduce this rather striking term, consciousness physics.
Yeah, that term definitely grabs your attention. We should probably clarify upfront, this isn't making a claim about, subjective awareness in the algorithm.
Right, it's a model.
It's a mathematical model for how an advanced search or cognitive process might work. And the core idea of consciousness physics here is that the agent's internal states, its focus, its memory, its search strategy aren't fixed.
They're not static parameters.
No, they're dynamic. They oscillate. They change over time according to specific harmonic functions, like waves.
So the agent itself has moods, or modes, a rhythm of attention and strategy.
That's a good way to think about it. It's intelligent state, pulses and shifts. And the key to peak performance, according to this model, is something called predictive phase alignment.
Predictive phase alignment, meaning
Meaning the agent can't just react to the problem landscape as it finds it. It needs to anticipate. It needs to predict the best time to use certain strategy based on its own internal rhythm and maybe even the inherent rhythm of the problem space itself.
so if the model predicts it's heading into a searching phase, it should adopt a searching strategy.
Exactly. Policies that predict these future mode distributions they found vastly outperform agents that just react. You have to sync up with the system's underlying rhythm.
Okay, and this anticipation is implemented through 4 specific modes of operation, right? M0 through M3. Let's get into what these actually are.
Right. These modes represent different styles of searching or processing information. M0 is called the solid mode.
Solid. Sounds focused.
Very focused. Think
Like-
meticulous, deep, local exploitation, like a librarian carefully examining one shelf. It has very low memory decay. It remembers exactly what it just saw nearby. High precision, but very little exploration outside its immediate focus.
Okay, so M0 drills down. What's M1?
M1 is the liquid mode. It's still pretty local, but it introduces some randomness, some stochastic local search, a bit more flexibility than M0. It allows for small variations, preventing it from getting totally stuck on one tiny path. Memory decay is moderate.
Still exploring nearby, but with a bit more wiggle room.
Yeah. Then comes M2, the gas mode, and this one is really critical.
Gas sounds expansive,
Yeah.
maybe chaotic.
Exactly. M2 is about wide-ranging, high-energy exploration, almost chaotic search, jumping across the solution space, and its defining characteristic is high memory decay.
High memory decay, so it forgets things quickly. Why is that good?
It's strategic forgetting. It deliberately lets go of recently explored, potentially suboptimal paths. This is mathematically essential because it stops the agent from getting trapped in a local optimum, a pretty good solution, but not the best one.
Ah, so forgetting helps it break free and explore totally different areas.
Precisely. If you just stick to M0 and M1, you might find a decent valley, but you'll never know if there's a much deeper valley over the next mountain range. M2 provides the necessary chaos to ensure global exploration to make those big leaps.
It sacrifices short-term memory for long-term discovery. Okay, that makes sense. What about M3?
M3 is the golden mode. This one's a bit more esoteric. It's designed for super efficient exploitation once promising structures are found.
Golden, like the golden ratio.
Often, yes. It seems to activate when the search pattern starts to resonate with fundamental mathematical structures like the golden ratio or Fibonacci sequences, which pop up in optimal paths in many natural and geometric systems. It's like finding a known highway through the solution space and traveling it efficiently.
So M0 drills, M1 wiggles, M2 jumps, and M3 follows the highways.
A pretty good summary. And the agent has to constantly shift between these modes. But it's not random shifting. It's governed by this dual objective.
Okay, what's the dual objective?
One objective is obvious. Maximize the information score. Find good cuts. Find fair divisions.
Makes sense. Get the best answer.
But the second objective is to maintain harmonic coherence. The agent's internal rhythm of switching between M0, M1, M2, M3 needs to stay in sync with the underlying rhythm of the problem space itself.
Why is fighting the rhythm bad? Why does it get penalized?
Because, as we saw with the modular rhythm engineering, the prime necklace problem itself has this inherent harmonic structure. Trying to force, say, an M0 deep dive when the system dynamics are suggesting an M2 exploratory jump is inefficient.
That's like trying to swim upstream.
Exactly. You expend more computational energy for less information gain. The system mathematically rewards agents that predict and comply with its natural ebb and flow of exploration and exploitation.
So the agent's internal cognitive state needs to phase align with the external mathematical state of the problem. That's fascinating. And did this actually work in practice?
Oh yeah. The validation numbers were pretty striking. This predictive harmonic controller achieved a plus 59% improvement in the final information score, meaning it found much better solutions compared to a purely reactive agent that didn't predict or align its phases.
Wow, nearly 60% better just by managing its nocturnal strategy rhythmically.
It's a huge difference. It really demonstrated that modeling this search process not as a fixed algorithm, but as this dynamic, oscillating, predictive system is incredibly powerful for these kinds of complex, nonlinear problems.
Do they see any specific patterns emerge?
They did. The agents spontaneously developed these complex but efficient metacycles of behavior, cycling through the modes M0, M1, M2, M3 in optimized loops, which further validated the framework's strategic power. It wasn't just random switching, it learned optimal sequences.
Okay, we've gone from just counting beads, basically combinatorics, to these sophisticated rhythm-based intelligent search strategies. Now we make another major pivot. We're heading into quantum mechanics territory.
This is where we need to translate everything into the language of operator theory.
Why? Why leave the relatively intuitive world of bead positions and cuts for abstract operators?
Because physics, especially quantum physics and condensed matter theory, doesn't really talk about static positions. It talks about states, operators acting on those states, Hilbert spaces, Hamiltonians. To connect the prime necklace to things like superconductivity, we have to adopt that language. We need to describe the dynamics and the energy of the system.
Okay, so how does the mapping work? What becomes what?
All right, so the actual prime positions on the necklace, they get formally treated as fermionic electron sites.
Like spots where an electron could be.
Okay, and the gaps between the primes, those are treated as fermionic hole sites, places where an electron isn't.
Ah, so it creates this alternating pattern, like matter and antimatter, almost.
Sort of. It creates a bipartite graph structure, a system of alternating site types. And that structure is fundamental for modeling lots of physical phenomena, definitely including superconductivity.
Okay, positions become electron sites, gaps become hole sites. What about the cuts we were making?
The cuts are no longer just breaks in the necklace. A cut at a specific position, say $6, is now represented by a mathematical object called a rank 1 operator, denoted to operator.
Operator. Something that acts on the state of the system.
Exactly. And what these teams operators do, mathematically, is they induce pairing amplitudes between the electron sites, primes, and the hole sites, gaps.
Pairing amplitudes, like creating connections or interactions between them.
Precisely. If you have a whole set of cuts, $2, the combined effect of all these induced pairings is captured in another key object, the pairing operator, delta.
Okay, so the collection of cuts defines this overall pairing interaction. And this immediately leads to a really profound claim, that this whole system defines a genuine, discrete, non-commutative space.
What does non-commutative actually mean here? It's a fundamental concept. Non-commutative means the order in which you do things matters.
Like multiplication.
Right.
2 times 5 is the same as 5 times 3. That's commutative.
Right. Standard geometry, like moving on a grid, is commutative. Go 5 steps east, then 3 steps north. You end up in the same place as going 3 north, then 5 east.
Okay.
But here, with these cut operators, tjtel followed by tir is not the same as tjel followed by tjtel. So tjtel, tj.
Why does the order of cuts matter?
Because making a cut table first actually changes the state of the system. It alters the pairing environment. So when you then apply tjel, it's acting on a different system than if you had applied tjel first. The effect isn't reversible just by swapping the order.
Well, okay. The cut operators don't commute. And that non-commutativity, that's a formal mathematical hook needed to connect this whole prime necklace thing to non-commutative geometry, or NCG.
That's the absolute prerequisite. The algebra generated by these cut operators forms a non-commutative algebra, which is the foundation of a non-commutative space.
So how do we understand the dynamics, the energy, within this weird non-commutative space defined by prime cuts?
For that, we borrow a really important tool from quantum theory, the Bogolyubov-Degenis, BDG Hamiltonian. We denote it Athram BDC because it depends on the set of cuts, C-stallers.
Okay, BDG Hamiltonian. What is it normally used for in physics? Why bring it here?
In standard physics, the BDG Hamiltonian is the workhorse for describing superconductors. It models how electrons form Cooper pairs, and it describes the energy states, the excitations, the ground state of those paired electrons.
The fundamental matrix of superconductivity.
Pretty much. And for our prime necklace, we construct this A-therm BDG matrix using 2 main ingredients. A baseline dynamics matrix for the system, let's call it HLI dollars, and crucially, that pairing operator, delta C, that encodes the effect of our cuts.
So it takes the basic necklace structure and adds the specific interaction pattern created by the cuts.
Exactly. It essentially translates the geometric act of cutting the necklace into a quantum energy signature.
And the reason this isn't just like a loose analogy is because of something called the exact spectral identity. This is a mathematical proof,
Yeah.
right?
Yes, this is a rigorous theorem they proved. It's not just similarity, it's an identity. It states that if you calculate the trace of the BDG Hamiltonian squared mathrm TSE22, which relates to the overall energy scale,
Okay.
that value is mathematically equal to some constant value plus a factor times the Frobenius norm of the pairing operator, squared. So delta F22.
Oh, okay. Let's unpack the Frobenius norm of the pairing operator.
Yeah.
What is that measuring in, like, plain English?
The Frobenius norm here, delta F22, it's basically measuring the total strength or intensity of the cuts. It sums up the magnitude of all the pairing interactions induced by all the individual operators in your set of cuts. Nothing else.
The theorem says that the overall energy levels of this quantum-like system, described by the BDG matrix spectrum, are directly and precisely tied to the total strength of the cuts we made on the necklace.
Exactly. It's a direct, proven mathematical link. The geometry of the cuts dictates the spectrum of the Hamiltonian. The mathematics of dividing primes is, in this specific framework, algebraically identical to the dynamics described by a quantum Hamiltonian.
That's a huge bridge. It confirms the connection is deep and structural, not just a metaphor.
It's the mathematical bedrock that allows the superconductor analogy to become much more concrete.
Right. So once that exact identity between the cut strength and the BDG spectrum, math from BD, was nailed down, these parallels between the prime necklace math and actual superconductivity math just jumped out, didn't they?
They really did. The structural analogies become almost eerily precise.
Okay, let's list them. What's a core phenomenon in superconductivity?
It's the formation of Cooper pairs, right? Pairs of electrons that bind together and move without resistance.
Okay, Cooper pairs. What's the parallel in the prime necklace?
The parallel is what they called antipodal cut solutions. These are specific pairs of cuts, often located on opposite sides of the necklace, that seem to work together synergistically to achieve perfect fairness. They are like bound cuts that enable zero imbalance.
Ah, so pairs of cuts working together, just like pairs of electrons. Makes sense. What else?
Well, the ultimate state in a superconductor is phase coherence. Everything lines up, resistance drops to zero.
The ideal superconducting state.
The direct parallel in the necklace problem is achieving the fair division condition. That means zero imbalance for all prime colors. You could call it achieving zero fairness resistance.
Okay, zero resistance maps to zero imbalance. That fits. What about the energy?
This is where it gets really striking. In physics, the Ginsburg-Landau GL energy functional is used to describe the energy landscape of a superconductor. Finding the minimum of this functional tells you the stable superconducting states.
Right, nature seeks minimum energy.
Well, the mathematical imbalance functional, let's call it phi-dollar, that they used to measure how unfair division was on the prime necklace. It turns out to have a mathematically identical structure to the Ginsburg-Landau functional.
Wait, identical structure, not
That's
similar.
Identical functional form. Minimizing the imbalance $5 to find the fairest cuts is mathematically the same process as minimizing the GL energy to find stable superconducting states.
Wow, okay. Now, you mentioned the Riemann Zeta function earlier. That gets woven in here too, right? It wasn't just for show.
No, it plays a crucial role. They refine the imbalance functional $5 by incorporating the zeta function. This creates a zeta-corrected segment weighting factor, dii pi I.
Okay, Pios is the prime value. Price comes from the zeta function. What does this factor do?
Think of it like adding an impurity potential in a real material. Primes are not uniformly dense small primes, like 2, 3, 5, or bunched together at the start. This weighting factor effectively penalizes segments of the necklace that contain lots of these small, densely packed primes.
Why penalize them?
It helps to smooth out the energy landscape. It accounts for the inherent irregularity of the prime distribution itself, making the minimization problem better behaved. This refined functional is called Zeta.
So Zeta is the ultimate measure of fairness energy, tailored specifically to the weirdness of prime numbers.
Exactly. And it was when they compared this optimized fairness energy to the binding energy calculated from the quantum BDG Hamiltonian that they stumbled upon the big twist.
The Anti-Superconductor Revelation.
This is maybe the most counterintuitive finding of the whole deep dive. In a normal superconductor, described by math from BDG, when the binding energy goes down, meaning the electron pairs are more tightly bound, more ordered, the material becomes more superconducting. Stronger binding equals better superconductor.
Makes sense. Lower energy, more stable state.
But for the prime necklace, when they plotted the BDG binding energy against the fairness energy, the Zeta, they found a strong anti-correlation. The correlation coefficient was around 59 oprics, mana 0.633.
Anti-correlation, meaning when one goes down, the other goes up.
Precisely. When the BDG energy decreased, suggesting stronger quantum binding, more order in that sense, the fairness functional Zeta actually increased.
Meaning the division became less fair.
Exactly. The system was moving away from the optimal fairness state when its quantum binding energy got stronger.
So the prime necklace system is using the exact same mathematical machinery as a superconductor.
The BDG Hamiltonian, the Ginsburg Landau-like functional.
But it's optimizing for the complete opposite goal.
That's the conclusion. A superconductor wants maximal binding and minimal spread. It wants electrons clustered into Cooper pairs for zero resistance. The prime necklace, in its quest for perfect fairness, inherently seeks maximal spread and maximal anti-clustering. It wants to distribute the prime colors as evenly and widely as possible across the dollar divisions.
So maximizing fairness looks like minimizing quantum binding from the BDG perspective. It prefers statistical dispersion over consolidation. It's an anti-superconductor by nature.
It highlights this fascinating idea of dual optimization. The underlying mathematical structure, the algebra, the Hamiltonian, sets the rules of the game, but the objective function you're trying to minimize or maximize determines the outcome. Here, the goal is maximum fairness, maximum spread, which is the antithesis of superconducting order.
And it wasn't just an analogy, right? They found evidence of actual collective quantum-like behavior.
Yes, applying the BDG framework wasn't just for show. It led them to discover a discrete superconducting phase transition right there in the prime necklace system.
A phase transition, like water freezing to ice.
Analogous to that, yes. They looked at the density of cuts applied to the necklace. Let's call it Orr's goal. When this density crossed a certain critical threshold, the BDG energy gap, which is like the energy needed to break a Cooper pair or create an excitation, suddenly opened up. It went from zero or small to a finite value, sharply and discontinuously.
And that sharp opening of an energy gap is the classic signature of a phase transition in many body quantum systems, like superconductors.
Exactly. It confirmed that this abstract mathematical system, built from primes and cuts, genuinely exhibits collective behavior and undergoes a phase transition into its optimal state, which, in this case, is the maximum fairness anti-superconducting state.
Wow. So the primes themselves, under this mathematical lens, obey laws akin to quantum phase transitions. That's pretty mind-blowing.
It really grounds the analogy in concrete, measurable phenomena within the model.
Okay, so we've established the prime necklace acts like an anti-superconductor, using quantum math but optimizing for spread. Now, the final ascent, tying this all together with the really big gun, non-commutative geometry, NCG.
Yeah, this is where it connects to the work of Field's medalist Elaine Kahn. NCG is this incredibly ambitious mathematical framework. The dream is that it might unify general relativity, gravity, with quantum mechanics.
The holy grail of physics, basically.
Pretty much. Kahn's idea is that maybe at the Planck scale, the very coordinates of spacetime, like x, y, z, t, don't commute, 6 lambda milers might not equal times $6 at that fundamental level.
Just like our cut operators didn't commute.
Exactly the same principle. The big challenge with Kahn's NCG is that it usually deals with infinite dimensional mathematical spaces, which makes it incredibly abstract and really hard to test or calculate things with.
Right, hard to get concrete predictions.
But the truly astonishing claim in this research is that the prime necklace system, this finite, discrete thing we built, provides a calculable test bed for these super abstract NCG principles.
How do you prove that this necklace game fits into such a grand theoretical structure like NCG?
You have to show that it satisfies the core axiomatic definition of NCG, which is something called a spectral triple, usually written as $2 HD.
Okay, spectral triple, 3 components, A, H, D. What are they in our necklace context?
We actually have them already from the previous steps. A stands for the algebra.
That's the algebra generated by our non-commuting cut operators.
We established that algebra back in part 3. It's non-commutative, which is key.
Okay, A is covered. What's H?
H is the Hilbert space. That's the space of possible states of our system.
And that's the space built from our prime positions, electron sites, and prime gaps, hole sites.
Yeah.
The fermionic states.
Exactly, the states that the operators act upon.
Got it. A and H are done. What's the crucial third piece, D?
D is the Dirac-like operator. This is the central geometric object in a spectral triple. It defines the metric or the distances within the non-commutative space.
And in our system, what plays the role of D?
Our old friend, the Bogolyubov-Digenis Hamiltonian, H method BDG, it acts mathematically like the Dirac operator for this specific discrete space. It maps states in the Hilbert space H, and its spectrum encodes the geometry.
So the claim is that the prime necklace system, defined by Dori H, Dor D, where A is the cut algebra, H is the state space, and D is the BDG Hamiltonian, actually satisfies all the complex mathematical axioms required to be officially called a spectral triple.
That's exactly what the research demonstrates. It's a concrete, finite, discrete example of a spectral triple.
But wait, NCG and spectral triples are supposed to describe fundamental physics, space-time, maybe gravity. How can a finite necklace made of numbers truly reflect those infinite continuous laws?
Yeah, that's a crucial point of clarification. The claim isn't that the necklace is a tiny piece of space-time.
Okay,
The point is that the mathematical structure and the algebraic rules required to solve the problem of finding a perfectly fair division on this necklace must adhere to the same fundamental principles that define a spectral triple. It suggests these NCG axioms might be universal mathematical laws applicable to finite discrete systems just as much as to infinite continuous ones.
so the underlying logic is the same, even if the scale and context are different.
Exactly. And this leads directly to the spectral action principle.
Another key Kohn idea.
Yes. Kohn proposed that the fundamental laws of physics, like the Standard Model plus gravity, might be derivable from a single principle, minimizing something called the spectral action. This action is calculated purely from the spectrum, the eigenvalues, of the Dirac operator, dollars.
Minimize this spectral action and the laws of physics pop out.
That's the grand vision. Now, here's the absolute stunner from the prime necklace research. Remember our refined fairness functional, the one derived from Ginsburg Landau and corrected by the Riemann Zeta function?
Yeah, the measure of unfairness we wanted to minimize.
It turns out that Zeta has the exact same mathematical structure as Kohn's spectral action when applied to this specific spectral triple Euler HDT.
Whoa, hold on. So the purely number-theoretic goal of minimizing unfairness on a prime necklace is mathematically equivalent to satisfying the fundamental geometric principle of minimizing the spectral action in this non-commutative space.
That's the claim. Minimizing theta is implementing the spectral action principle for this discrete NCG.
That's an incredible convergence.
It really is. This shocking equivalence led the researchers to coin the term Su-Kohn duality. It highlights this duality between two seemingly completely unrelated worlds, optimizing prime number distributions and the fundamental geometry of NCG proposed for unifying physics. They arrived at the same mathematical blueprint from opposite directions.
Su-Kohn duality.
Okay.
And this all culminates in one master equation.
Yes, the spectral trace identity, which they identify as the unified Lagrangian L for the entire prime necklace system. This single equation essentially describes the total energy or action of the system, and minimizing it finds the optimal faircuts.
A Lagrangian, like in physics, that contains everything.
Yeah.
What are the pieces woven into it?
It's beautiful because it explicitly shows the synthesis. If you look at the terms that make up dollars, you see, first, a term directly from NCG derived from the geometry of the prime graph, like a Laplacian. That's the structural foundation.
Okay, geometry first.
Second, a term representing Shannon entropy from information theory. This term naturally promotes divisions that are balanced and spread out high entropy states.
Information theory pushing for fairness.
Third, a term incorporating the Riemann Zeta function from number theory, encoding the unique irregular distribution properties specific to the primes.
Number theory adding its specific flavor.
And finally, the Ginsburg-Landau functional, borrowed from superconductivity theory, acting as the core measure of fairness, energy, or imbalance.
So the Lagrangian dollar is literally NCG plus H plus Zeta plus eta. To solve the simple-sounding necklace puzzle, the system has to simultaneously satisfy constraints from non-commutative geometry, information theory, number theory, and condensed matter physics.
It's an extraordinary unification, all packed into finding fair cuts on a circle of primes.
Okay, this is a lot. We've gone from beads to unified Lagrangians via anti-superconductors and non-commutative geometry. These are incredibly ambitious claims. They can't just hang there as abstract theory, right? What did the actual computational results show? Was there rigorous validation?
Absolutely critical question. And yes, the validation was extensive and seems quite robust based on the sources. First, consistency. that consciousness-guided search framework we discussed. It consistently found the optimal or near-optimal solutions 91.7% of the time across many different necklace sizes and parameters. So the method is reliable.
Okay, the search algorithm works well.
Uh,
What about validating the big theoretical claims, like the NCG connection?
That was the core validation. They needed to check if minimizing the spectral action from NCG really was the same as minimizing the fairness functional Sato.
The Sukan duality claim.
Exactly. They calculated both values for many different sets of cuts. The result, a near-perfect correlation, consistently greater than 0.999 between the NCG spectral action term and the theta functional.
0.999, that's basically identical.
For all practical purposes, yes. Minimizing one is minimizing the other. It strongly validates their equivalence and the deep connection between the fairness problem and the NCG framework for this system.
Wow. Okay, that's compelling. And you mentioned earlier the discovery of that discrete superconducting phase transition using the BDG Hamiltonian.
Yes, that's another piece of validation. Finding that sharp opening of the BDG energy gap at a critical density of cuts confirmed that this system exhibits genuine quantum-like collective behavior. It's not just analogy. It follows the rules of phase transitions.
Okay, strong theoretical and numerical validation. What about the practical side? Did this fancy consciousness-guided, harmonically controlled search actually offer an advantage over simpler methods?
A massive advantage. Think about finding the best cuts by just trying all combinations brute force.
That would explode right, exponentially hard.
Totally infeasible for anything but the tiniest necklaces. The number of ways to cut grows incredibly fast. But this new approach, the one guided by the harmonic principles and the underlying structure.
The one that aligns with the system's rhythm.
Exactly. It achieved an empirical computational complexity of roughly O log n for finding the optimal solutions, where n is the number of primes.
Logarithmic scaling. That's insanely efficient. That means you could solve it for practically astronomical numbers of primes.
It's the difference between impossible and easily tractable. It shows the power of discovering and exploiting the deep hidden mathematical structure of a problem. Understanding the geometry and dynamics dramatically reduces the search cost.
Okay, so let's boil it all down. If someone listening has followed us through primes, topology, consciousness physics, operators, BDG, NCG, anti-superconductors, what is the single most important insight, the aha moment, they should take away from this entire deep dive?
I think the core insight, the real mind bender, is this. The apparent randomness, the seeming chaos in how prime numbers are distributed, it might not be disorder at all.
It's not noise.
It seems to be a kind of perfect quantum order, but an order optimized for the exact opposite of what we usually look for. It's optimized for anti-clustering, for maximum fairness, for maximum statistical spread.
So all those failed attempts over centuries to find simple patterns or periodicities in primes, they failed because people were looking for the wrong kind of pattern.
Exactly. They were looking for regularity, for clustering, for simple harmonic waves, maybe like the order in a crystal or a traditional superconductor. They were looking for consolidation, for binding.
But the primes are fundamentally about dispersion.
Their distribution, when viewed through this modular index lens, seems algebraically designed to achieve maximal fairness across different classes. It's an optimal configuration for spreading things out as evenly as possible, and that perfect statistical balance looks like random noise if you're using tools designed to find simple clustering.
So the chaos is the order, but it's an order optimized for fairness and spread.
That seems to be the profound takeaway. And this entire study effectively creates a cross-discipline dictionary. It provides concrete mathematical proof that concepts from abstract number theory, like prime distribution, and concepts from condensed matter physics, like superconductivity Hamiltonians, literally share an operator language and an underlying algebraic structure via NCG.
And you mentioned the significance for NCG itself.
Yeah, perhaps the biggest intellectual contribution is providing this finite, discrete, calculable testbed for Alain Cohn's non-commutative geometry. NCG is incredibly powerful but very abstract. This gives physicists and mathematicians a concrete playground built from simple primes where they can actually compute spectral actions, test NCG principles, and potentially gain insights relevant to the much harder problem of unifying physics. It suggests the fundamental unity of mathematics might be even deeper than we thought.
It implies these underlying rules about operators, spectra, non-commutativity are truly universal.
It really suggests that the mathematical laws governing systems that optimize for binding and order, like superconductors, and systems that optimize for spreading and fairness, like the primes, apparently, might just be two sides of the same fundamental algebraic coin. Sometimes the difference is just a minus sign in the objective function you're minimizing.
Incredible. So this whole journey started with a seemingly simple puzzle about dividing a prime-weighted necklace fairly.
Yeah, it seemed almost like a kid's game.
And it's taken us through topology, predictive AI models, non-commuting operators, quantum Hamiltonians, anti-superconductivity, phase transitions, and ultimately landed us at a unified Lagrangian, rooted in the deepest structures of non-commutative geometry.
The elegance of the synthesis is really quite breathtaking. It's powerful evidence, I think, that sometimes what looks like irreducible complexity or chaos in nature, or even in abstract math, might just be a very sophisticated form of hidden order, waiting for the right lens, the right mathematical language to reveal itself.
Okay, so we've learned that the primes, far from being truly random, might exhibit a perfect quantum order designed for maximum fairness and spread. Here's a final provocative thought for you, the listener, to chew on.
Okay.
If the prime numbers, these fundamental building blocks of arithmetic, are governed by these deep principles of dual optimization and non-commutative geometry, maximizing dispersion, instead of binding what else out there looks random but isn't. Think about other complex systems, maybe traffic flow, ecological population dynamics, even economic fluctuations. Could some phenomena that appear chaotic actually be optimizing for some kind of maximal spread or balance, following a hidden spectral action principle we haven't recognized yet? What other parts of the universe might be secretly maximizing their fairness?
It definitely makes you want to look again at things we've dismissed as noise. Keep searching for that deep pattern.
Absolutely. We'll leave you with that thought. Catch you next time for the next deep dive.